All right, let's talk about something you use every single day. Ever stop to wonder what's really going on inside your speakers? How do they keep that bass thumping and the cymbals sounding so sharp? Well, the secret is this tiny, unsung hero of the electronics world, the filter. Seriously, it's a key part of pretty much every piece of tech you own, and today we're going to pull back the curtain and see exactly how it works. Right. Think about your favorite song for a second. You've got that deep, thumping bass line, the really crisp, high-pitched cymbals, and then the singer's voice somewhere in the middle. How on earth does a simple speaker box know to send the right sounds to the right places? What stops it all from just turning into a chaotic, muddy mess? Well, the answer is a really elegant piece of engineering, the electronic filter. You can think of it as a little traffic controller for sound, or for any signal, really. Its whole job is to decide which frequencies get the green light and which ones get stopped dead in their tracks. So let's dive in and see how this thing actually pulls it off. So at its very core, a filter is basically a selective gatekeeper. That's it. Its only job is to look at the frequency of every single signal that tries to pass and decide, are you on the list? Can you come in? So the official term is a frequency selective circuit. And this is possible because the components inside, things like capacitors and inductors, have this natural built-in reaction to frequency. A capacitor, for example, just lets high-frequency signals zip right through but really puts the brakes on low-frequency ones. A filter just arranges these parts to take advantage of that natural behavior. So every filter is defined by two key zones. You've got the passband, which is like the VIP list. These are all the frequencies the filter says, yep, you can come on through. Everything else gets thrown into the stop band. Frequencies in the stop band get seriously weakened, or as engineers like to say, attenuated, so they basically don't have any impact on the output. Okay, but how does the filter actually draw that line in the sand? How does it decide where that passband ends and the stop band begins? Well, it all boils down to one single crucial number. And that number is called the cutoff frequency. Just think of it as the exact point on the frequency dial that acts as the boundary line. It is hands down the most important setting we use to describe what a simple filter is supposed to do. Now, here's a little detail. In the real world, this cutoff isn't like a brick wall. It's more like a slope. So engineers needed a super specific point to call the official boundary. They chose what's called the half-power point. The cutoff frequency is the exact point where the signal's power is cut in half, which also happens to be where its voltage drops to precisely 70.7% of its original strength. Okay, now that we've got the basic lingo down, we can meet the four major families of filters. And each one is really just defined by where it decides to put its passband and stop band. It's that simple. First up, we've got the two most fundamental types. A low-pass filter does exactly what it sounds like. It lets all the low frequencies through, like the bass from a subwoofer. And a high-pass filter? Well, it does the exact opposite. It blocks out the low stuff and lets all the high frequencies, like treble, get through. They're perfect mirror images of each other. Then we get a little more specialized. A bandpass filter is like a super selective gatekeeper. It only lets a very specific, narrow band of frequencies get through. And its opposite is the band reject filter. People often call this a notch filter because it's designed to carve out and block a very specific, unwanted frequency, like that annoying 60 Hz hum you sometimes hear from electronics. So we know what they do, but how do you actually build one? For these simple low-pass and high-pass filters, it's kind of shocking how few parts you actually need. A basic low-pass filter? It takes just two little components, a resistor and a capacitor. It's called an RSC circuit, and when you measure the output voltage across the capacitor, you've got yourself a low-pass filter. So why does that work? Well, a capacitor is kind of like a tiny reservoir for electricity. It takes time to fill up and empty out. This has the effect of smoothing out and resisting those fast, high-frequency signals while letting the slow, low-frequency ones pass right on by. Okay, get ready for this, because this is the magic trick. You take that exact same circuit, same resistor, same capacitor, hooked up the same way. But instead of measuring across the capacitor, you measure the output across the resistor. And just like that, the whole thing flips on its head. It's now a high-pass filter. Isn't that wild? The same two parts can do two completely opposite jobs. I mean, that's just an incredible piece of electronic elegance right there. All right, what about those band pass and band reject filters? Since they're way more precise, they're targeting a very specific range of frequencies, we just need a couple more terms to describe how they behave. First up is bandwidth. This one's pretty straightforward. It's just how wide the range of frequencies is that the filter is either passing or rejecting. You just subtract the low cutoff frequency from the high one. Simple as that. The second one, and this one's maybe a little more interesting, is the quality factor, or just Q. You can think of Q as a measure of how picky or selective the filter is. If you want to get mathematical, it's just the center frequency of the band divided by the bandwidth. So here's the key takeaway. A high Q factor means you have a really narrow bandwidth. If you were to draw the filter's response on a graph, a high Q filter would look like a super tall, sharp spike, right? It's isolating a tiny little sliver of frequencies. A low Q filter, on the other hand, would look more like a broad, gentle hill, affecting a much wider range. Okay, let's wrap this up with a few real-world design notes. The simple filters we've been talking about are called passive filters because they only use passive parts like resistors and capacitors. And that means in the real world, they have some important limitations you have to think about. So there are three really key things you've got to remember. First up, because they're passive, these filters can only ever reduce a signal strength. They can't boost it. The gain is never going to be more than 1. Second, they're a bit sensitive. If you hook up something like a speaker to the output, engineers call that a load, it'll actually change how the filter behaves. It can even shift that cutoff frequency we talked about. And finally, and this is super cool, there's this deep connection between time and frequency. Remember how we said the capacitor charges up kind of slowly? Well, that has a name, the time constant. And it turns out the cutoff frequency is just the inverse of that time constant. They're literally two sides of the same coin. From tuning a radio station to shaping the exact sound of an electric guitar, filters are these silent gatekeepers that bring order to this whole world of signals. So now that you know the basic rules they play by, what kind of signals would you want to filter?